we're talking rotations. We already did those big ideas through the Algebruh things. Okay, so remember, we're always going to keep our big ideas in mind. And so one thing we kind of pointed out are that there are two ways that we can turn objects. We can turn them clockwise, right, which would be like this direction, so the way a clock goes, or counterclockwise, which would be the opposite direction, or the opposite way that a clock goes. A lot of times in math, I don't know the reason, but that is the default a lot of times. But you can make sure if you want your math communication tight, that you're always just saying clockwise or counterclockwise. And then there are two D's for rotations. Two things you need to know. We need to know the degree, that is how far. And today we're going to focus on 90, 180, and some 270. All right, and you have to know which direction, and that's going to reference that clockwise, counterclockwise. That'll tell us which way to go. All right. So one thing I want to ask, and remember I can't see you guys while I've got this screen overlay, is are they going to be congruent, and how do you know? So I'd like a volunteer to unmute and tell me, do you think they'll be congruent, and how do you know?
They will, because it's the same, it'll be the same distance away, and the shape won't change.
I like how you explain things that we saw in the warm-up, right? We noticed all the points would be equidistant from the origin that we spun it around. So yeah, if all the points seem to stay distance away, that means in relation to each other, they're the same distance away, which means they will have the same size and shape, which means they're congruent. We're just spinning it. We're not changing what it is, right? So you're going to be able to do something that I can't do that I think is pretty useful. So we're going to rotate this triangle ABC. I'm going to highlight it red right now just so it pops. We're going to rotate this. And one thing you can do is we're going to start by 90 degrees counterclockwise. Remember, that gives us how far in which direction. And one thing that you can do that's really cool is you can put your pencil down on the origin, and then you can spin your paper a quarter turn. So I'm actually going to try something here, kind of interesting. So you can spin your paper a quarter turn. It's not going to let me do it. And what you'll see is if you imagine spinning a quarter turn, your y-axis will now be your x-axis, and your x-axis will now be your y-axis. So you're going to spin a quarter turn that direction. And those points, that is where your new triangle would be. That new triangle would be at point -4, 1. That's where your A prime should be. Your B prime point would be at -2, 5. And your C prime would be at 0, 2. All right? So I want you to be able to make sure you can do that quarter turn on your paper from the origin. You can kind of see I went 90 degrees that direction for my quarter turn. All right? And the new points, and I can't show the spin, but if you like put your pencil right on the origin and quarter turn your paper to the left, your original triangle will look like it's right here in the second quadrant. All right? So I just want to write down our ordered pairs real quick. The A prime was at point -4, 1. The B prime point was at -2, 5. The C prime point at 0, 2. And our originals were 1, 4, 5, 2, and 2, 0. And you should see a pattern here. Can anybody tell me the pattern they're seeing from our original points to our new ones? What's a pattern that you're seeing? That's pretty cool. And you might remember yesterday we did like XY becomes this thing. So what's the pattern you're seeing?
The first number is either the first number in the pair is like kind of swapped.
Yep.
And then it becomes positive.
Or the opposite, right? So swapped Y. It's whatever the Y value was, but it's opposite. Great.
I have a question about one of them, though.
Oh, wait. It is not whatever the Y value. Yeah, it is whatever the Y's value was, but opposite. And then the X the x became in the y. So what's the question? So next we're going to work on the 180 from the original. Okay, I'm going to change. Uh-oh. I just got rid of that. My bad. My bad again. So now we're going to do 180 from the original. Let me give you the original points again. And I was going to change color. So I had 1, 4, 2, 0, and 5, 2. Okay. So 180 from the original, and I'm going to call this one A double prime, B double prime, and C double prime. All right, and you could kind of see where this is going to go, and I might actually run out of room with my screen share. You're going to see where this goes by putting your pencil at the origin, doing a 180-degree turn. All right, and what you'll see is you're going to end up with points -1, -4 for A double prime, -5, -2 for your B double prime, and -2, 0 for your C double prime. And this would be your new triangle. You'll notice it's like if you turned your paper half the way around, that's where your original would end up looking, right there. I really like the ability to turn my paper. I think it's nice. Now, oh, I never wrote down what C double prime was. C double prime, I got -2, 0. So that's my new points. Now, if I had my original xy, the rule I can write here from my original, 1, 4 became -1, -4. 5, 2 became -5, -2. Who can explain that to me? What the pattern is?
Everything's the opposite.
The opposite. So -x, -y. And we also saw that yesterday when we did a double flip, when we flipped over the x and then the y, or over the y and over the x. So that's cool. That's real cool. All right, now let's do our 270. We'll do an orange. We'd have A triple prime. So 270 would be a 3/4 turn. So again, you could put your pencil at the origin, 3/4 turn to the left, and see how things look. That's going to put our point at 4, -1. 1, 2, 3, 4, -1. That's going to be our A triple prime. 2, -5 for B triple prime. Oh, right on the edge. That's B triple prime. And C triple prime is going to end up at 0, -2. And that's our new triangle for a 3/4 turn. I did it in orange here. All right. And you're going to, again, notice a pattern from the original. So if our original is xy, this one up here, right? If our original is xy, and what's happening here, you may notice, we're going from 1, 4 to 4, -1. So y is going in the first spot, and x is going in the second spot, but as the opposite. So I'm not going to have you, again, you're not going to memorize the rule. You're not even going to use the rule on the test. I just want you to be able to see it. On the test, what you're going to have is like 2 triangles, and I'm going to say what kind of transformation happened and how do you explain it. So you'd have to say like the degrees. So don't think too much into it. Don't worry too much. Don't memorize the XY stuff. I'm just getting you some information right now, all right? I kind of want to draw that second one on there again just because I think you can see how it's like the quarter turn when I had that one here. We lost it from the screen share, though. All righty, so that's rotations, friends. So direction and degree. There are rules there, but again, you're going to be working on paper or you're just going to be seeing a visual. I love putting my pencil on the origin and turning it. That's the best visual for me. Let's talk about dilations. I think, I was just telling you about how it messes with your eyes when the doctor dilates your eyes, right? And you can think your pupil was like this, and then it becomes that big, right? It makes your pupil bigger. Well, that's because a dilation means that we're going to get an image that's the same shape. Okay? But a different size. So this is our first transformation that is not a rigid transformation. All of our other transformations, it was the same exact size and shape. This one, not the case. So the word that we're going to use in math for that is instead of congruent, we're going to use similar. And the word similar when we're talking math means like the sides are going to hold the same proportions. So you see dilations all the time. Every time you pinch, zoom on your phone to see something bigger, or pinch zoom out to see something smaller, that's a dilation. All right? And you guys should know this from last year, scale factor. This is a ratio. And I like to use a little different. Instead of image length and pre-image length, I like to do like fake. I use the fake to real ratio a lot, which is like, that's the new to the old, fake to real. So that works really well with scale models, scale drawings. I always use that ratio, fake to real. We already learned from our big ideas that greater than 1, Miles told us, gives us something that's larger when our scale factor is greater than 1. And when it's less than 1, it gives us something smaller. We already know that. When we multiply by a number less than 1, we get an answer that's smaller. All right? So here's the rule for scale factor. We're going to multiply to get new pairs. So if the factor is 3, that's just saying xy is going to change by 3 times the x and 3 times the y. It's actually one of the easiest transformations to kind of write out because you just multiply your ordered pairs. So not even looking at a graph, we're looking at, or a table, or graph. If I'm going to apply a scale factor of 4 to here, who can unmute and explain the rule to me first? A scale factor of 4, I'm going to change x and y by what? Who can tell me how? I need someone to unmute and tell me what I'm going to do here. Example 2 is a lot like example 1 for the rule.
You're gonna multiply each coordinate by 4?
Yeah, x and y are going to be multiplied by 4. So here are my new points. A prime, if I multiply everything by 4, I get a 0 and an 8. B prime, who can give them to me? Someone else. I think that was Oliver. I can't tell. Someone else, give me B prime.
16.
Thank you. So times 4 times 4. Someone else, give me C prime.
Negative 4, 16.
Excellent. So what happens is you're going to multiply all your points by that, and this is a dilation over the origin. And even if I don't draw it out, what do I know about my new picture? Compared to the old one, it's going to be what? Bigger or smaller?
Larger.
It's going to be larger, yeah, larger. You can see just by looking at the points that they're going to be more spread out. Okay, so let's check this out. So that last one, we showed something getting larger. This time we have a scale factor of 1/2. So who can give me my rule? How is xy going to change?
Multiply by 1/2.
Yeah, so 1/2 times x, 1/2 times y. Let's see what happens. So for point P, I have negative 2, 4. Who can give me my new coordinates?
Negative 1, 2.
Thanks. You guys are doing a great job spreading that around, especially since I can't see it. So that's P prime. Negative 1, 2. And let's do this too. Negative 2, 4 was our original point. Negative 1, 2 is our new point. All right. Let's take a look at Q. My original points were 4, 4. Q prime, I need someone to give them to me.
2, 2.
2, 2. It's what I like to wear on the weekends, right? So 4, 4 was our original point. New point is 2, 2. Okay, number R. Letter R. Yeah, I hear somebody.
Well, I was just going to ask, like, you wrote, like, X, Y, but is that just, like, a communication thing? Because, like, sometimes there are more than 2 coordinates, right?
Yeah, no, there's only one ordered pair. This would be for each point in your figure. Right, so I'm applying this rule to every xy for the figure. Yep, good question.
Okay.
Who can give me my R prime?
2, negative 1.
There we go. So I had a 4, negative 2. And 2, negative 1 is going to be my new one. Last point, S prime, or S. We had negative 4, negative 4. S prime, who can give it to me?
Negative 2, negative 2.
Excellent, negative 2, negative 2. And you can already see what's happening here, I think. Negative 4, negative 4. So my original is this outer one right here. And my new one is half the area of that right there. One thing that's kind of fun, you don't have to do it all, but if you go like this, that's called like the point of dilation. It goes through all the points where your original and your new one are. It's kind of fun. So we could one place I want to show you right here where we can prove that they're similar. Does everybody see that right here, that edge, that line is 3? And this one's 6. And right here, we have another that's 3 and 6. So the ratio of original to new, I'm going to rewrite that. New to original, fake to real, is 1/2, which is also our scale factor. Right? That's not coincidence at all, but it's a great way to check. So this is telling us that we know that they are not the same size, but that they are similar. But what looks true about their angles?
And you're out of here, buddy. Give me that shotgun. Austin just went down.
Somebody's watching Family Guy while we're doing this?
Right now with real gameplay after the action of the great officer.
Someone was just watching Family Guy. I heard that. You guys heard that?
I heard something.
Yeah, I heard something. All
That
right.
was my brother.
Come on, bro. All right.
Sure. It was my brother. Sure.
I believe you. So, what do we notice about the angle measures? Do they look the same or different? Like this angle and this angle, same or different?
They're the same.
They're the same. Because otherwise our proportions wouldn't stay the same, all right? So that's all I think that we need to know. Actually, let's just look at the example 4 rule real quick, okay? I got to get out of here. All right, so let's just make a rule for number 4. Let's say we have x, y. Who can tell me the rule?
Wait. On my page, example 4 and 5 are both missing.
Yeah, I got
All right, let's just look at my
Yeah,
example
just
4.
get from 3 to 6.
Okay.
Let's just look at my example 4. What's my rule here?
2.5 x and 2.5 y.
Yeah, 2.5x, 2.5y. I prefer to just rock that fraction, but they're both the same. Maybe it's easier for you to multiply by the decimal, right? All right, last thing I want to check out. I need help writing the rule. Oh, first of all, is this going to get bigger or smaller? That top one.
Bigger.
It's going to get bigger, 2.5 times bigger. So it's an enlargement. Now down here, I want someone to try to give me the rule for x, y. So really what we need to find is the scale factor. Remember that the pre-image has no prime on it, and the image, the new one. So this is old, this is new. So right there should tell us our scale factor is smaller, right, than 1. So I want someone to go out on a limb and tell me what they think it is. How much smaller?
A third?
Yeah, so this one's kind of hard because there isn't like a definitive spot that you can, without using a distance equation, but we can measure origin to like right there. That's 2. And then origin up there, that's 6. So 2 to 6, we're going to have a scale factor of 1/3. And that would give us our dilation of the thing that's 1/3 smaller. And it works because that point of dilation goes through all of those angles. All right, friends, that's everything we need.